Welcome back everyone to another video in our FE Civil Preparation course. In this video, we are going to talk about soil bearing capacity. In our last video, we mentioned that there are two main failure mechanisms for foundation, which are bearing capacity failure or excessive settlement. In this video, we are going to discuss more in details about the bearing capacity failure. There are three main modes of failure for bearing capacity. First one is general shear failure, which is the most common mode of failure and it occurs in strong soil. Let me talk first about the third mode of failure, because the second mode is actually a combination between the first and the third. So the third mode of failure is punching shear failure, and it occurs in loose sand, while the second mode of failure is actually a combination between both punching shear and general shear failure. Now we are going to learn about one of the most important equations in geotechnical engineering, which is the Zaggy equation for bearing capacity. We use this equation to calculate the ultimate bearing capacity for any soil. The equation is Q ultimate equals C NC plus gamma effective dF NQ plus half gamma effective BN gamma, where NC is the bearing capacity factor for cohesion, NQ is the bearing capacity factor for depth, N gamma is the bearing capacity factor for unit weight, dF is the depth of footing below ground surface, and B is the width of the strip footing. There are two cases for bearing capacity calculations: in case of water table is below the foundation level, and in case of water table being above the foundation level. In case of water table is below the foundation level, then our equation will remain the same with no change. And in case of water table is higher than the foundation level, as we can see here, the only difference is going to be that we will separate the soil into two parts, the higher part above the water table and the lower part below the water table. For the upper part, we will use the gamma dry of the soil and multiply by its depth, while for the lower part, we are going to use the gamma effective, which is the gamma saturated minus the gamma water, and multiply it by its depth. This equation actually is going to be pretty easy once we start solving some examples. There are different expressions that we must understand about soil bearing capacity. First is the ultimate bearing capacity, and this is the bearing capacity as calculated from the Zaggy equation, and it doesn't take into consideration any safety factor. Second is the net ultimate bearing capacity, and this one is the ultimate bearing capacity as calculated from the Zaggy equation minus the weight of soil backfilling above the foundation level, which equals to gamma multiplied by D. Third is safe bearing capacity, which equals to the ultimate bearing capacity divided by the factor of safety, which is normally taken as 3. And fourth, and the most important expression, which is the net safe bearing capacity, and it equals to the net ultimate bearing capacity divided by the factor of safety, and this is the value which we use in the foundation design. So now, let's have an example on this. So let's check this example. We have this foundation here, as we can see, with 5 meter width. The angle of internal friction is 33, and the soil coefficients NC, NQ, N gamma are as shown here. And we want to calculate the ultimate bearing capacity for this footing. So the ultimate bearing capacity, it will equal C NC plus gamma effective dF NQ plus 0.5 gamma effective B N gamma. The C NC equals 0, of course, because this is sand, and the C equals 0 for sand, plus the gamma effective. The gamma saturated here equals 19.1, so the gamma effective will equal 9.1 multiplied by 4, which is the depth of this foundation, multiplied by 21.2, which is NQ, plus 0.5 multiplied by 9.1, which is gamma effective, multiplied by B, which is 5 foot, multiplied by 23.1, 5 meter, sorry, not 5 foot, multiplied by 23.1. So all of this will equal 1297 kilonewton per meter square. So the answer is B, which is the closest answer, which is 1300 kilonewton per meter square.